Welcome everyone to this Quintus Technologies webinar. My name is Anders Magnusson and I work for Quintus in Västerås, Sweden, and I'm very excited presenting this to you and look forward to an inspiring Q&A after the presentation. We will be looking into the possibilities for advanced ceramics that comes from using high pressure heat treatment and steered cooling, and what this means for the ceramics and applications that we have in focus. I will try to summarize and give you some main takeaways before we go to the question and answer section. This webinar is pre-recorded, so please write your questions in the webinar tool for us to go through in the live Q&A afterwards. I want to start off by highlighting our knowledge center and our YouTube channel, so please go into those and find anything you need to know about Quintus Technologies and all kinds of isostatic pressings. So let's start exploring what possibilities Quintus HIP system brings to the field of advanced ceramics. This is, of course, what we firstly think about when we're talking about hot isostatic pressing for any material, really. That when we want to remove pores and voids, we go for hot isostatic pressing. We can use up to 2000 bars, 2000 degrees centigrade, and close most any pore and voids in most any material. However, there are other possibilities also that Quintus has developed over the years and which we now think it's time also to explore for the advanced ceramics. So the first thing, of course, when using the HIP, we want to make sure that we get the best possible material that we can have by closing all the pores and voids. But now we also want to look into how we can increase the productivity when hipping, and also what can be done when it comes to in-hip tailoring of material properties. How do we increase hip productivity? Well, of course, the best thing is to reduce the cooling step, not giving any value to the hipping process. And we can do this with a soft steered cooling, which will allow us to keep the integrity of also ceramic materials and bringing the cooling step to 1 hour or less for most hipping cycles. Well, how do we achieve this? Well, Quintus have developed the high pressure heat treatment strategy for our HIP systems. And this is, of course, a very nice functionality to have for nickel-based superalloys, titanium alloys, aluminum alloys, and so on. But now we're looking into how can we use this also for advanced ceramic materials. This is a demonstration cycle from our latest generation of uniform rapid cooling, URC. We run this cycle showing the customer what their system can do when it's been installed. And as you can see with this one, we have been rapid cooling 225 kilos of steel bars in this system. And we can do this at 1700 kelvins per minute cooling rate. That is, of course, way too fast for most ceramic materials, not to say all ceramic materials. But with this system, we can control the cooling rate anywhere between 0 and 400 kelvins per minute, adapting it to the needs for the specific ceramic system. So, as an example, if we would do a controlled steered cooling at 20K per minute from 1450 degrees centigrade, the cooling segment would be only 40 minutes long. A natural cooling of a load like this could take 8 hours, or if you have a monoblock system, it could take even longer. So of course, there's a lot of potential for productivity increase using this functionality. Okay, so how do we go about using this uniform rapid cooling? Well, actually, we need to start off by defining what cooling rate we would like to have, and also what cooling rate we can have when it comes to thermal shock sensitive ceramics. Then we can set this cooling rate in the cooling segment of the HIP cycle and run the cycle accordingly. Of course, there's a difference on what temperature we are reading inside the system and what temperature the components have at each given time. So what we are actually doing is that we are programming what cooling rate the gas inside the HIP system should have. And we need to transfer that to the cooling rate in the components. One way of doing this is, of course, using the state-of-the-art system that Quintus has developed when it comes to controlling the HIP system from the actual temperature inside the component itself. And this is done by inserting a thermocouple into the component and telling the HIP system to run the segments according to the temperature inside the component. The cooling curve from doing a run like this, you can see in this graph. We will have a cooling rate inside the component to the set cooling rate, in this case 30 Ks per minute. You can see that the gas temperature, which is the furnace temperature, needs to be cooled off significantly faster. And at the same time as the temperature drops during the cooling, also the pressure will drop. So this kind of investigations we can support you with in our application centers in Västerås, Sweden, and in Columbus, Ohio, USA. And new for 2022, we are setting up these possibilities also in the application center in Takasago, Hyogo, Japan. So if we're going to do rapid cooling of ceramic materials, we need to know the material properties and see how well it will respond to a fast cooling rate. And of course, we need to have low thermal expansion, low wall thickness, high thermal conductivity, high strength is always good, of course, and a low Young's modulus. The geometry features of the components will also, of course, matter. And if we have large stress concentrations, we need to be aware of that, of course. So looking at different ceramic systems, we can see which ones we can say is simple to do rapid cooling with, and which ones we need to take more care with materials like silicon nitride, silicon carbide, and of course aluminum nitride will be very easy, while when it comes to zirconia, which has a very high thermal expansion coefficient and very low thermal conductivity, there we will of course need to take care. So at Quintus we're doing calculation using fluid dynamics and finite element, and to see what kind of stresses that we will get in the components. We have a snapshot of running uniform rapid cooling of a silicon nitride sphere being 51 millimeters in diameter, and maxing the cooling rate of the HIP system using the URC furnace in our application center. To the left, you can see how the temperature will distribute in the system, and we can then from that look into how the temperature will distribute inside the individual component, using that data in the finite element calculation to find the stresses. And of course it will be the stresses on the surface that will be of most interest. And when running this cycle, which is more or less the toughest condition that we can get from this, we see that we just merely get tension stresses in the surface. Of course, due to that we have more than 100 megapascals of residual pressure in the system compressing the components. So, focusing on some advanced ceramics material system. Of course, in the family of advanced ceramics, we have a lot, hundreds and thousands probably, of different material systems, which are oxide, nitrides, carbides, borides. And of course, it's the polycrystalline systems that are of most interest when it comes to hipping. So, of course, we need to look into silicon nitride and ball bearings, since that is booming at the moment with EVs and windmills and any electric motors where there is an issue with electrical arcing and electrical corrosion. So, what we need to enable is the densification of also micrometer-sized pores and voids to make sure that we have the best possible strength, toughness and reliability of the ceramic ball bearings. We also, if we would like to have the possibility to tailor the grain boundaries, it could be that we want to have good high temperature properties, or that we need high thermal conductivity. Of course, we need to prevent that the nitrides are dissociating at high temperatures. We need to prevent silicon oxide gas evaporating from the component surfaces, so we don't end up with snowflake defects in the surface that will need extensive grinding. Powder beds have been widely used when sintering without pressure to avoid the dissociation of the nitrides. We can't have the powder bed, of course, if we want to utilize the uniform rapid cooling in the best possible way. And also getting rid of powder from the HIP system will reduce cost of maintenance and cleaning, of course. So, we want to make sure that we support the best practice in hipping, so we can enable the powder bed free hipping of silicon nitride and also other materials. One big benefit of using high pressure atmosphere in the hip is, of course, that we can stack components on top of each other without risking them bonding together. When hipping silicon nitride and also other nitrides using nitrogen gas in the hip system, we will of course have a lot of possible chemical reaction between gas and solid that we want to avoid. One thing is, of course, that we don't need silicon oxide leaving the component surfaces. And of course, we don't want the graphite heater to corrode away from the reaction with the nitride and with oxygen and water vapor inside the system. We elaborate a bit more on this in the white paper for silicon nitride, so please look into that if you have more questions. The other ceramic system very much popular at the moment is the zirconia toughened alumina, used for medical implants for our hip and knee joints. In this case, of course, the first thing is that we want to make sure that we densify the pores and voids. We need high strength and we need high reliability for components going into our body. We also, when the volumes now are increasing, need to make sure that we optimize the productivity. And we see that we can have cooling segments also in these HIP cycles of 1 hour or less. So when it comes to CTA, of course, we need to prevent phase transformations taking place during a fast cooling. And this could be the case if we have surface cracks and we cool too fast, bringing tensional stresses to the crack tips. But of course, if we have calculated the cooling rate and we are using the steered cooling of the URC, we should be fine also for CTA, or we know that we will be fine also with CTA. Another very important area for hipping is, of course, when it comes to polycrystalline transparent ceramics, used for lasers and detectors for X-rays, as armor material, for lenses and so on, where you need to densify all pores and voids to get down to hundreds of a percent in porosity before you have the optimum transparency. Using the uniform rapid cooling, you can of course also increase the productivity in this process, and also play around with crystallinity and amorphous grain boundaries, for instance, doing the uniform rapid cooling. So what's in it for me? Well, of course, we want to have a reduced cost per component. We get an increase in HIP utilization, we cut the lead time for hipping, we reduce scrap due to pores and voids, and using best practices and avoiding the powder bed, we will have less hip maintenance and wear of the hip system. And with the Quintus hips, we can also reuse the process gas over and over again. So what are we looking for when it comes to tailoring the properties? Well, of course, it's the 0% porosity and voids, and also the possibility to tailor the grain size, crystal structure, grain boundaries, also for ceramics, precipitates. We want to optimize strength and toughness, corrosion properties, and surface roughness. So when it comes to quality assurance, well, with the hip and the hipping, we get a robustness, of course. We have a reduced scattering properties for the components of the hipping. And using a hip system where we can control temperature and pressure and cooling and heating rates, of course, that will ensure that we will have a good product. And also reduce the need for final inspections, non-destructive testing, batch testings, and so on. We also have the option to be able to do gas analysis of the system gas continuously. Looking at materials and process development, of course, cutting the cooling segment will give us a buffer for increasing volumes in the hip. We will have the possibility to develop new and existing materials and components using the uniform rapid cooling strategy, and perhaps also we will have the possibility to improve the properties also for cost-sensitive components previously not possible to hip. So this brings us to the end of this webinar, and I want to take the opportunity again to push for our Knowledge Center, where you will find these 3 white papers dealing with the ceramic materials in focus. Let's move on to the Q&A.